good chat. I'm thinking I might be able to at least get through this frequency domain specifications, and maybe start getting into steady state error on Monday. But in all likelihood, I don't think I'll be able to include a bunch of steady state error on the final. But I'm going to try and cover it as much as I can on Monday if I get to that, which would be great. And steady state error is, I wish I would have jumped on that one. I wanted to move it up earlier, especially because we do cover it a little bit in some of the labs, but I'm digressing again. So, getting back to this next topic is the frequency domain specifications. So we're looking at the frequency response shaping, or the loop shaping. You may have recognized I mentioned this loop shaping in the practice midterm, and because I hadn't actually mentioned it in class, I was hoping you guys would ignore that one, but I felt like that on the practice midterm was not quite fair. I was just looking to see what you guys would answer for that. Getting back to this though, controller design comparison. So our design specifications in the time domain, we have things like the rise time, settling time, overshoot, steady state error, etc. We've covered most of that except for steady state error. But I hope at least from the labs you've taken at this point, you at least recognize what steady state error is. Maybe not how to calculate or figure out what it will be, but at least recognize that steady state error is a shift from a disturbance in our steady state output. And we want that to maintain a certain output. So our approximate translation for desired closed loop pole locations in the S domain is to be our root locus shaping. And then we have our desired open loop frequency response in the S domain, which would be our loop shaping and frequency response shaping. So getting back to a basic feedback controller design, we right now are just doing a simple feedback with no sensor. So we have our controller in our plant. Open loop here is the plant times the controller, and then the closed loop would be the open loop over 1 plus the open loop. Hope you guys are all very familiar with it at this point. So given the plant, we would design the controller that would satisfy the closed loop stability, time domain specs, i.e. the transient steady state response. We learned that typical qualitative relationships between the open loop Bodie plot and the closed loop properties, such as stability and time domain responses. So just reviewing, and we've covered this in the past few weeks, so the Bodie plot of a series connected plant 1 and plant 2 is the addition of each Bodie plot of G1 of plant 1 and plant 2. So the gain plots can be added together and our phase plots can be added together. We use this property to design the controller so that the gain times the controller has a desired shape for that Bodie plot. So here's, this is the general idea of a lot of the things we're going to be covering here. So starting off, so your typical modifications of our open loop Bodie plot. We're going to cover first steady state accuracy. We'll get into sensitivity, disturbance rejection, our transient response speed, the relative stability, and I mentioned it a little bit, noise reduction earlier this hour. We also have the relative stability, which we're familiar with from the phase margin, and we can also consider our transient overshoot. So this plot right here, I'd say be kind of familiar with. I'm thinking of putting some questions in that might kind of ask you to identify some of the things that we can modify using our open loop circuit, or open loop Bodie plot here. So I'd probably give you what I'd probably identify A, B, C, D, E, each of these areas, and then ask you, okay, we want to adjust our steady state accuracy. What area of the open loop Bodie plot should we be looking at? Just to give you an idea of some questions that I'm thinking of there. But getting back into what we actually need to cover. So we're looking at the steady state accuracy first. So for steady state accuracy, we want the gain to be high for those lower frequencies. So if we have a high gain at lower frequencies, it's also, if we look back at the lead compensator with the integrator, adding that integrator, we actually increased our low gain or low frequency gain, which helps with that steady state accuracy. So, and again, looking over this real quick, a large magnitude of L for our frequency response function. If we have that very large values, we would get this magnitude of the whole system to be approximately 1, or sorry, magnitude of our of the characters. When he changes the lettering, we would call this our loop gain. Oh, I forget the name of it right now. But if we have a large magnitude there, obviously, if this is very large and this is very large, we'd be getting approximately 1. So the YT tracks RT composed of the low frequencies very well. Again, we're assuming these are low frequency responses where we have a large magnitude gain. We're continuing here, so we're looking at the step response. So if we have an increase here, we take the L of 0, we're looking at the initial value. So the limit is S approaches 0, so that's L of 0. If we have a high gain, then we have high accuracy in this case. We're responding to our ramp input. We would need to have at least one integrator for KB to be a finite value. Obviously, if you look at this, if L of S has one integrator, that would cancel out, leaving us with a finite response there. And again, it sucks because maybe I'll get into the KP, KB, and KA values a little bit more with the steady state slides that I'll probably get into, but at least to have a vague familiarity with some of these responses. And if we're looking at a parabolic input, we would have the increase of KA to the initial value theorem. Using initial value theorem, we would see that because of this S squared being here, we would need at least 2 integrators in our system for the parabolic response to show good steady state accuracy. Yeah. Most of the things we're testing, especially when we're describing things with our lab, we're trying to put a step response in there. But it's important to recognize some of these too, especially with the steady state accuracy. And hopefully I get pretty far in the steady state error, but let me not digress more. Okay, so we've kind of checked off just generally what we're looking for, that steady state accuracy, is we want our gain to be high for low frequencies. Now we're going to look at the transient overshoot, and this applies more to the phase area over here. So if we're looking at this, again, same illustration here, we have a controller implant with no sensor. GSCS, gain, or plant times the controller. We'd have a form of omega n squared over S times S plus 2 zeta omega n, which gives us our general, oh man, so bad with words today. General formula for our loop gain here. So what we care here, and while we're bringing this up, is in this transient overshoot. I mean, we covered it a little bit previously with our time response, but you can see how the damping ratio can help affect our closed loop step response. But you can also see from some of these additional plots how the change in our damping ratio can change our open loop Bode plot for the magnitude response and for the phase response. So we see here with a higher damping ratio, we get more oscillations that take more time to settle out, but also our phase margin decreases much more rapidly, leaving us less phase margin and causing more percent overshoot. You also see we end up with higher gain, which if we're designing for that steady state accuracy would be good, but it takes a lot longer to settle out. Questions on that for now? And percent overshoot, we're relating that to our damping ratio, but looking at that specifically on a Bode plot for magnitude and phase. Lower damping ratio would result in more behavior that would show a smaller phase margin. Okay, so now we're going to look at the relative stability. So we could say that we're looking at relative, well, I guess we already covered relative stability to a degree, gain margin and phase margin here. So we require adequate gain margin, phase margin for safety against inaccuracies in modeling and reasonable transient response. So it's like we just mentioned with the overshoot. And I've mentioned this a few times already, it's reasonable numbers. We're looking somewhere between, I would say, phase margin 45 and 60 degrees would be reasonable, especially with our approximations. And gain margin, we'd say usually between 6 and 10 dB. And it says here. But if we have good phase margin, it usually leads to good gain margin. But I also want to reiterate, we can have good phase margin without having a positive gain margin. It is possible, and it'll probably get brought up later, but I want to just reiterate that just because you might see negative gain margin does not necessarily mean that we are not stable. Hint, hint. So now we're moving on to our transient response speed. So we're looking at right around where our crossover frequency is. So for a fast response, the magnitude gain would want to be at a higher crossover frequency. So if we have, phrase that better, I don't like that wording there. We want a larger gain crossover frequency to give us the faster response. I guess this kind of illustrates it a little bit. So here we set our damping ratio to just 0.3. Yes. And then we have 3 different frequencies, natural frequencies that we're going to use here. Our lowest frequency, omega n equals 1. Right about there. We see that it has a slower response, which is taking, I don't know if this is in seconds, but almost 15 seconds to start to settle out. So that's probably about the 2% settling out. I guess this would be 2%. But it takes a lot longer. If we have omega n crossing over at 2 radians per second, we can see that increases dramatically here. And then when we go to 3 over here, we end up seeing that we have a much faster response. So if I asked you a question about if we wanted to improve our response speed, the answer to that would be we want a larger gain crossover frequency, which, if you remember from about an hour ago, we described we chose that 5 kilohertz when we did our design for that phase boost. So if we weren't, and I guess just to relate this with, if we weren't worried about some of the other high frequency responses, we could set that to 10 kilohertz, which would result in a much faster response speed. But we would have other trade-offs to give in there too. But just pointing this out because I wanted to point out that we chose our gain crossover frequency when we did our Bode plot design. Next, we're going to get into noise reduction. So for noise reduction, we should have a low magnitude gain at higher frequencies. So you can see here, at the higher frequencies, if we have low gain at that point, if we have more of a runoff, so we've got, let's see, if we're going to have the choice between minus 20 dB per decade or going to higher order and minus 40 dB per decade beyond our crossover, we would probably prefer, if we want noise reduction, to have that minus 40 dB per decade, which is not on those slides anymore. Which also factors in for how long we want to have that phase boost that we put in with our design. So if we, again, decrease that phase boost, frequency Z and frequency F of P, we would end up with that would end up with lower phase boost, depending on that's what we're designing for, but we would end up reducing some more of the noise because we would have less of that gain bump, I guess you can call it, that occurs in that phase boost area. That makes sense. I don't have anything to physically show that, but I want to relate it to what I've kind of been talking about the past hour before. Let's see, next we're looking at disturbance rejection, sensitivity. So for sensitivity reduction, it indicates the influence of the plant variation. So something to keep in mind: temperature, humidity, how old this plant is, and how that might affect our closed loop performance. So here we have a sensitivity function, partial derivative of each. We end up with 1 over the loop gain. Sorry, LS. Yeah, we're back to using that as the loop gain. We're switching between the L and the T. For sensitivity reduction, L should have, again, it relates also to our steady state accuracy. Disturbance rejection, having large gain at low frequencies, is helpful for reducing the sensitivity. I know I brought this up previously. Disturbance signal in general, it's a change in our output load is what we're doing with our lab, but it could be any unwanted signal that enters our system. So examples given here: load change for a voltage regulator, wind turbulence in the airplane altitude control, a wave and ship direction control. I'm not sure. Wave and ship direction control? Not sure what he meant by that one originally. Sudden temperature change outside of a controlled room. So we had this room closed, and then, I don't know, the rest of the building got knocked down, and then suddenly the wind comes whipping in. They're all disturbance signals. So for disturbance rejection, we have a very similar. If we want disturbance rejection, we want to have large gain at the low frequencies. So YT is not affected by the disturbance signal here because of the large gain in our low frequency response there. So you can see as this gets larger and larger, this would be, say we have 1 over 10 here, that'd be 1 over 11 total. If we increase this gain here to, say, 100, that's less than 1% versus less than 10%. So larger gain results in more disturbance rejection. Actually, I forgot how, this specific lecture was actually a lot quicker than I thought it would be, which is good. I'm actually happy there. So, just a summary here. But you can kind of see on, this might be something nice to put on your cheat sheet, just a general breakdown in just this slide. If we're looking to increase the steady state accuracy, sensitivity, and disturbance rejection, we want to bump up our low frequency gain, shown here. If we wanted faster transient response speed, we would move our crossover frequency to a higher value. We want relative stability. If we're looking at specifically here, relative stability for the gain margin, we would have a larger gain margin. And if we want to have noise reduction, we would want our high frequency response to be lower. Getting back to relative stability, looking at the phase margin, if we have a higher phase margin, we end up with more relative stability. We also, if we have a higher phase margin, we'd end up with, we're looking to deal with transient overshoot. A higher phase margin will also result in less overshoot. So, frequency response, the loop shaping design is done using the compensators. Controller compensator. So, summarizing this, the system performance, such as transient response and steady state error, time domain attributes, and sensitivity to plant variations and disturbance rejection are addressed by appropriate design in the frequency domain. This leads to a set of frequency domain specifications that we can look at, and these are specifications are on the loop gain, specifically low frequency gain, bandwidth, phase margin, and high frequency roll-off. Nice. Again, there isn't much in this that I'm expecting you to calculate, so a lot of these functions I wouldn't worry too much about. What I'm concerned about with this specific lecture is recognizing what areas of the Bode plot to look for and to adjust if you're looking to shape a lot of these frequency domain specifications. Questions on that? Let's see, do I want to get into... Yeah, I mean, I didn't review it a lot, but let me go ahead and get started on the steady state error. Just get some of this preliminary stuff and refreshers out of the way. All right. So, I might actually make it to the final lecture. Hopefully by the end of Monday. I'll try and leave a little bit of time on Monday too, if I can, to answer final questions about the lab write-up if necessary. But I'm actually kind of confident now after getting through that. And actually maybe I'll just make more time for review. But, so, getting back to time response. So we'd like to analyze the stable systems property by applying a test input, R of t. Described this previously a few times, and observing the output response, y of t. So, covered this a few times, but the time response is divided into two sections. Our transient or natural response, which as time increases to infinity, this would die out to 0. And the steady state, which is our forced response, is our output at the steady state. So after the transient dies out, what are we left with in our system? So this is kind of the example we used previously for the time response. So we have the transient response of this system is equal to the, this specific system, to the unit step is negative 0.8 e to the negative t over 2. So this will, as t increases, this will continue to die out. Then we're left only with our steady state response, which should continue as long as we have power here. Typical test inputs, covering these again really quick. We have our step function, which is usually the most popular. We're doing a sudden increase at t0 to, for the most part, we're using 1 there to keep things simple. We have our ramp function, which is our u of t, which as we increase with time, we increase our r of t. And then we have the parabolic function. So we're increasing, as time increases, we're increasing more and more. at a higher rate. And sinusoidal inputs was dealt earlier with the frequency response. So when forming our frequency response function, we're putting in, that's where we derive our frequency response function from the sinusoidal input. So it would be a special case of our output response. So for the steady state value for the step input, we're supposing for this example that the plant G of S is stable. So by our final value theorem to the step response, again, remembering U of t transformed is 1 over s, depends on what the r value is. But final value theorem, limit as s approaches 0, these s's cancel out, so we're just left with I guess the amplitude of r times our system response at 0 frequency. So the step response converges to a finite value, which would be our steady state value, y steady state. And this should still be familiar. Here's our transient response, and our steady state. These are also our time domain responses here. Again, reminder here, we've got our rise time from 0.1, no, there it is, that was the 0.98, so 10% to 90% is our rise time. We have our peak overshoot here, 2% settling time, delay time, and Ymax. All things we covered previously in the time response. We're going to revisit this example. We can see the example in slide 4. It's the same example we've seen a few times. Our steady state error in this case, we're looking for, because we're using a unit step input, looking for 1, but we end up settling to about 0.2, or sorry, settling to 0.8. Which is 0.2 off of what our steady state is expected to be. So we have our performance measurements. We covered previously the transient response for peak value, time, overshoot, delay time, rise time, settling time, all of the above were time domain responses. Now we're going to connect these measurements in with the S domain to get our steady state error. So, looking at steady state error for the feedback, we're looking at system in this case with unity feedback. So there's no sensor, no block in our feedback path. Now suppose we want the output y of t to track r of t. So we want no error signal. So the error here would be r of t minus y of t. The steady state error would be the limit as the time approaches infinity of e of t, so, or the limit as s approaches 0 of s e of s. Again, following our final value theorem again, which I hope you're all still very familiar with. We are supposing in this instance that the closed loop system is stable. Important for this. So we end up with a limit here of s times 1 over loop gain r of s. In this case, because we don't have any feedback going on there. The error constants here, so the closed loop system ability to reduce steady state error. We have a large error constant, means a large ability for the steady state to deviate. So we have 3 error constants. We have the step error, position error. Now I remember the KP, KB, and KA. The position error constant, Kp, with the limit as s approaches 0 of L of s. The ramp error, which would be our velocity error constant, Kp, would be with the limit as s approaches 0 of s L of s. So we would need a integrator in there to get that to a, keep it from 0. And we have the parabolic error, which is our acceleration error constant, which would be the limits, again, s squared, so we need 2 integrators in there to keep that from going to 0. So steady state error for the step response here, we have RT is equal to the unit step times some constant. So therefore our error in steady state would be that constant over 1 plus whatever our KP is. We can calculate the KP, and kind of showing that right here, still expand it out a little bit more. So here's our system with nothing in the sensor, times R of S canceled out. This is where we end up getting our error steady state equal to R over 1 plus L of 0, which, L of 0, which would be our KP position error. If we're looking at a input of the unit ramp, you can see we have here's our input, and here is the output, which oscillates a little bit. But doing the same thing, we have the unit ramp would equate to, with Laplace transform, to whatever our amplitude is here, or constant, over S squared. And therefore our steady state error would be the magnitude of that input over 1 plus L of S squared. One of those gets canceled out, which still leaves us as R, which is a constant, over the limit as S approaches 0 of S over LS. Again, relating that to our velocity error. And again, just covering the parabolic. So we're saying that with a parabolic input, we end up with a steady state error equal to R, the input's amplitude, over Ka, where Ka is equal to the limit as S approaches 0 of S squared L of S. So if we want 0 steady state error, when does that actually occur? So infinite error constant for the step. Oh, we have infinite error if we have just a constant. So if we don't have an integrator in our system, so a type 1 system, we would end up with infinite error on our step response. If we don't have at least 2 integrators on a system of type 2, we'll get into the system types in a bit, we would end up, again, for a ramp input, we would end up with infinite error. Finally, for the parabolic input, if we don't have a system with at least 3 integrators, system type 3, we would again end up with infinite steady state error. Just covering a few of the basics here, but that's confused. I know there's probably a few things I still need to cover. I know system types will be coming up, or at least identifying them. But does this make sense for everybody right now, or follow-up questions to start? Get some of this stuff just covered. So this system, L of S, has 2 integrators, leaving us with a characteristic equation. This is just an example. The characteristic equation, 1 plus L of S equals to 0, would break down into S times S squared plus K, 0, and then expand it out, we'd end up with S cubed. Closed loop system is not stable for any K, so E of T will stable. This should be expanded on a little bit more. Something for me to come back to on Monday. I don't feel like that's it's not stable for any K. I'll get back to that. Is this just showing? Yeah, sorry, I'm not remembering these slides offhand. I didn't start to review these small steady state errors. Trying to see what he was getting at here. So we're saying that our plant has 2 integrators. So the closed loop is not stable for any value for this specific plant. The 2 will never converge. I'm not sure the point of pointing this out at the moment. I'll try and refresh that on Monday. Here, where he's getting to the fact that now he's using a different plant. What he was trying to get at putting these slides in here. But just for example, this specific system, instead of having 2 integrators, like this one, we end up with 1 integrator. And if we work out the Ruth-Hurwitz criterion, apparently we end up with K values that would be between 0 and 1.3. Still trying to see what he's getting at there though. Yeah, I'm gonna have to refresh my memory on these ones and come back to it, 16 and 17. See if I can move on from there. We've only got a few more minutes anyways. And of course, we're getting back to a 2 integrator system. We're able to show that the closed loop is stable using Ruth-Hurwitz. Therefore, in this specific system, steady state. Yeah, definitely. I'm gonna have to review these a little bit more. I am not sure what he's getting at with these 3 examples. Well, considering I'm stuck on these ones, I think this is about where I will call it for today. Do you have anybody have any questions on anything that we covered today previously with the design, specifically the 2 example compensators, and just starting on some of this steady state error?
You're gonna post lab 5, the updated version today?
I'm gonna try and get the, not midterm, practice final, the homework, I'm gonna get it worked on a little bit tonight, post it by tomorrow at the latest. I was planning on posting lab 5 by Sunday.